Yes, hello students. We are meeting this time again to share with you the lecture number 16. Lecture number 6, sorry. It is lecture number 6 on application of this linear differential equations with constant coefficients. We are doing at this time the cases when right side is 0. I have written here the example, the best example. This is important example is from your different books. It is L d2 theta by dt square plus g theta is 0, given that theta is equal to alpha and d theta by dt is 0 when t is 0. You will find out its solution. And second very important question that I have written here, this is in different books, especially in engineering mathematics. Show that the solution of the simple harmonic motion with damping proportional velocity given by x double dot plus kx dot plus mu x is equal to 0 is given by this. This is the solution given, where you are given n square is mu minus 1 by 4 k square, n being real, and dots denote differentiation with respect to t. There is also third one, very important application, but it may not be visible to you. I will write it again there when I reach here. It is d3y dx cube plus 6 d2y by dx square plus 12 dy by dx plus 8y is equal to 0. It is a boundary value problem when you are given that y naught is 0, y dash naught is 0, and y double dash naught is 2. We will solve these questions, these applications. Let me have the solution of this, solution of first part. Let me solve this. These are the solutions. Solutions we have to solve. It is L times d2 theta by dt square plus g theta is 0. You are given here, it is given that theta is alpha and d theta by dt is 0 when t is 0. You have to solve this differentially. So how we proceed is, we write this equation, this second order differential equation with constant coefficients in symbolic representation. What is it, is symbolic representation? It is symbolic representation is, you can write it is L d square plus g theta is equal to 0, where you have d is equal to d by dt. And note here you have dependent variable theta and independent variable t. So you have auxiliary equation here. Auxiliary equation is given by L d square plus g is equal to 0. This gives you that d square, L d square is minus g, which implies that d square is minus g by L. That means your d is plus minus iota under root of g by L, because this d goes under radical, this is iota. So your d is actually 0, real part is 0 plus minus iota root g by L. So when you write down solution is given by, you will write down the solution. Your dependent variable is theta, be careful about it. Dependent and independent value, this variable, sorry, it is theta is equal to, it is e raised to power real part is 0, independent variable is t. Then constant, you have to involve two constants because it is of second degree. You will write a cos of imaginary part of the complex number, it is this, under root of g by L into t, you have here t, because independent variable is t. Then plus b sine of root g by L into t, solution. So you can write your theta is e raised power 0, it is 1, it is only a cos root of g by L t plus b sine of root of g by L t. Root g by L is a constant here. I will rub it. So my solution is, I can write this solution in this way also. Theta is equal to A cos of 80 by writing this root of g by a, I'll denote with this by a. It will save you time in writing the solution, this solution. Finally, you will replace again a by root g by a. You can do it. It is b sine of 80. Where I have replaced it for the time being, I have put a is equal to root of g by a. Well, I am given here, this is your equation number second. This is actually the solution of this equation where a is this, but we are given boundary value conditions. We have to use using theta is equal to alpha and t is equal to 0. Your a and b, capital A and B are arbitrarily constants. These are arbitrarily constant. Note it. You may use C1, C2, no problem. So theta is your alpha. It is A cos 0 plus B sine 0. That is alpha is equal to A into 1. Sine 0 is 0. That means you have got one arbitrarily constant. A is given by alpha. You have got one arbitrarily constant. It is alpha. Well, I have now given d theta by dt is 0 when t is 0. Differentiate equation number second. Differentiate equation second with respect to t. This is d theta by dt. Derivative of this cos, it is minus sign. Derivative of angle with respect to t is a minus a. So it is minus a capital A sine of 80. Then here plus a capital B. It is a capital B is your arbitrarily constant. Sine is cos of 80. Derivative of cos is minus sine. Derivative of sine is cos. Angle. Derivative of angle is a. Now you will here use t0 when t is 0 and d theta by dt is given by what? D theta by dt is also 0. D theta by dt is 0 when t is 0. Well, it is 0 is equal to minus a sine 0 plus a b cos 0. That gives 0 is equal to a into b because cos 0 is 1. This gives me theta is alpha, yes, A is your alpha. It is AB. Yes, we have here a into b sine 0 is 0, then plus it is a b cos 0 is 1. A is not 0, this gives b 0. Okay, so we have got a alpha, b 0 using this in given solution. Using in second, we get the solution here. Now solution will be theta is equal to A is alpha cos 80 plus B is 0. Now you can use the value of A, it is root G by L. Therefore we have got solution theta is alpha cos of, it is root G by L T. This is the solution of this equation, of this differential equation. Then we were having the given conditions, theta is alpha, d theta by dt is 0 and t is 0. Let me have the second result, solution to second. This is a problem second, solution to second. Here you are given that show that the solution of the simple harmonic motion with damping proportional velocity given by this. It is, question is this, x double dot plus k x dot plus mu x. Mu x is 0, where you are given in the question. You have to prove the solution is this. You have to prove this is the solution. You have to prove this is the solution. And you are given the n square. The value of n square is given by mu minus 1 by 4 k square. This is the value of n square, and being the real. Dots denote differentiation with respect to t. When dots denote differentiation with respect to t, how we shall go? This means actually it is your d2x by dt square plus k times dx by dt plus, it is a simple harmonic motion in physics with damping proportional velocity. You will write it as symbolic representation is given by, it is d square plus kd plus mu times x is equal to 0. Okay, then you will write it as auxiliary equation. What is the auxiliary equation? It is d square plus kd plus mu is equal to 0. It is now quadratic in d. It will be d equal to minus k plus minus under root of k square minus 4 mu by 2. You can write this way, this also. It is minus k by 2 plus minus under root of, it is k square minus 4 mu by 2. If you bring this to in under radical, then it will be 4. This is d equal to minus k by 2 plus minus under root of k square minus 4 mu by 4. Because 2 is outside radical, when we take it inside, you can write it as 4. So this is equal to minus k by 2 plus minus under root of k square by 4 minus mu. Look here, you are given that n square is mu minus 1 by 4 k square. So that minus n square will be 1 by 4 k square minus mu. It is minus n square by given condition. This is your given condition, the value of n square. So your d is now minus k by 2 plus minus under root of minus n square. So this will be minus k by 2 plus minus iota n. It is a complex number now. So you can write it in this way, the solution. I don't need this. Well, it is now d equal to minus k by 2 plus minus iota n. It is a complex. So what is solution? What is your dependent variable here? It is x. It is x is equal to e raised power real part. It is minus k by 2. Independent variable is t. outside, then arbitrary constant. Let me write A because he has used the arbitrary constant capital A and capital B. Let me write arbitrary constant capital A, capital B. Capital A cos of what? Real part, the imaginary part of the complex. It is nt plus B sine of nt. So this is the solution. X is equal to, so it is x is equal to e raised power minus k by 2t, then a cos nt plus b sine nt. This is the solution of this differential equation with constant coefficients, but with the condition that n square was given by mu minus 1 by 4 k square and being real. Let me have one more example, then we will go to the second case when we have right hand side x not equal to 0. Let us solve the third one. It is not visible to you. I will write this problem number third. Solve. It is d3 y dx cube plus 6 d2y dx square plus 12 dy by dx plus 8y is equal to 0. You are given the boundary conditions here. He says like this: y0 is 0, y dash 0, it can be written sometimes this way, y dash 0 is also 0, and y double dash 0 is 2. These are the boundary conditions given. Let us first solve this, then we will use these conditions. It is symbolic representation is this. Symbolic representation. It is d cube plus 6d square plus 12d plus 8 into y is equal to 0. What is it? Is auxiliary equation. Your auxiliary equation is d cube plus 6d square plus 12d plus 8 equal to 0. I have already told you in case of cubic, biquadratic, degree 5, so on and so forth, when you have the auxiliary equation of such degrees, you will use the inspection method. By inspection method, you will test here by inspection, use d equal to minus 1, 1, minus 2, 2, and see which one satisfies it. Suppose I use d is equal to minus 1 here, it will be minus 1, then plus 6 minus 1 square, it is 1, then plus 12 into minus 1 plus 8. This gives minus 1, it is plus 6 minus 12 plus 8. It is 8 plus 6 is 12, it is 14, sorry, but it is 13, it does not satisfy it. Let me use now, positive 1 will not satisfy here, positive 1 will not work. Let me see test d equal to minus 2, d equal to minus 2. When you use d is equal to minus 2, it will be minus 8, it will be 4 into 24, this is here minus 12, this is plus 8, then this is 8 plus 8, this goes, it is 24 here, sorry, it is 24. We just look again, d minus 2, this is minus 8, this is 24, it is 10 plus 24, this is 12 into minus 2, 24, and this is 8, this goes, it is 0. Yes, you will write d is equal to minus 2 satisfied. So here, since d equal to minus 2, I have named it, I will name it first, satisfied equation first, auxiliary equation first, by testing, because I have already told you there are different methods of solving the cubic. One is coordinates. Biquadratic, there is Descartes, but you will not go to those rules. It will take time. So inspection is the best. Use this. If it does not satisfy, then this I have dropped. I have not tested because all the terms are positive. If they were the alternate term, I would use this one also. But I dropped one. I used -2. Then -2 has satisfied it. Okay. Then you have got this one root, d -2. How will write other? We apply synthetic division. We apply synthetic division by d equal to -2. Write all the coefficients. It is 1. Coefficient of d square, it is 6. It is 12. It is 8. Okay. Then you will use -2 here. 8 take 1 here. Cross multiply 1 into -2, -2. Ordinary add, it is 4. 4 into this is -8. Then it is 4 here. 4 into this is -8. Yes, it is 0. This should be 0 because it is the remainder. Remainder must be 0 when we take -2 as a root. So what is a reduced equation? A reduced equation is, your reduced equation is d square plus 4d plus d equal to 0. This is the reduced equation. D square plus 4d plus d equal to 0. So how you proceed? When you have d square plus 4d, you get d square plus 4d plus d equal to 0. You can write it, it is d plus 2 whole square is equal to 0. D square plus 4d plus 4, sorry. D square plus 4d, it is 4, I'm sorry. It is 4 here. It is 4. It is d plus 2 whole square. It is d, you get -2 here for this. It is d, this implies d is -2 repeated. So you have got 3 repeated roots. 3 repeated. It has 3 repeated roots. So when it has 3 repeated roots, you know how we write the solution in case of repeated roots. Well, their solution is, complete solution is y is equal to c1 plus c2x. 3 constants I have to introduce, but roots are repeated. c1 plus c2x plus c3x square. Then it is e raised power -2x. Name this equation, say it is second. Now you have to use these values. We are given, you see how we find out c1, c2 and c3. Very important. These 3 conditions will give you the this arbitrarily constant, then solution becomes particular solution. Now we are given what? y0, 0. What does this mean imply? This means your y is 0 when x is 0. This statement. You are using these values in statements also in this successive differentiation where you use through the application of Leibniz theorem. If you remember, application of Leibniz theorem. It is same what you did there. Okay. Use y0. It is 0 is equal to c1 x is 0 plus 0. This is e raised power 0. This gives me c1 is 0. So I have got one constant, c1 is 0. Next he says y dash 0 is 0. So this also means that dy by dx means y dash or y dash is 0 when x is 0. So for that I have to differentiate equation number second. Differentiate second. With respect to x, when I differentiate it, it is y dash, or you may say dy by dx, it is equal to derivative of c1. No, you will apply here product rule. Derivative of this, it is 0. It is c2 plus it is 3x c3. Then write e raised power -2x as it is. Be cautious, I am applying product rule. Then plus first function as it is c1 plus c2x plus c3x square. Then derivative of second function, exponential function, it is e raised power minus 2x, as is differentiation of power, that is minus 2, log of base, it is 1. I am writing this setup again in the top, on the top. I will write this here so that this may be visible to you. I am getting y dash, I am getting here y dash is c2 plus 3x c3, it is 3x c3 e raised power minus 2x plus c1 plus c2x plus c3x square, then it is minus 2 e raised power minus 2x, differentiation of second function. Now I have found c1 is 0. Okay, let me use here, use y dash 0, then x is 0, use it. It is 0, this is your c2 plus x is 0, this is 0, e raised power 0 plus here c1 plus x is 0, 0 plus 0, it is e raised power 0. You get here 0 is equal to c2 plus c1, but you have already found out c1 is 0, that means c2 is also 0. You have found c2 also. c1 you have got 0, c2 you have got 0. Remember that solution is here. This is our solution. I will name this equation now third, because I have to differentiate this again. I will name it third. Be cautious now when I differentiate this. Let me rub it. Well, it is differentiating this again. Differentiate equation third again. You will get y double dash, that is d2y by dx square. Here apply product rule. Derivative of this, it is only, this is 0, this is 3c3 e raised power minus 2x, then plus c2 plus 3x c3, derivative of this minus 2 e raised power minus 2x. Now we come here. I will rub it. It is c1 plus c2 x plus c3x square. Well, I will differentiate now this part. Derivative of this with respect to x, it is c2 plus 2 x c3, then minus 2 e raised power minus 2x as it is, then plus this as it is, c1 plus c2x plus c3 x square, then derivative of this part, the derivative of e raised power minus 2x is e raised power minus 2x, as the differentiation of power is minus 2, so this will be times e raised power minus 2 square e raised power minus 2x. Now you have to use here this x0 and y double dash is y double dash 0 means y double dash at x0, it is 2, it is given by 2, remember it is 2, so I will use this as 2, this is your 3 c3 e raised power 0, my x is 0, my c2 is 0, x is 0, it is 0, c2 is 0, it is 0, then plus c2 is 0, x is 0, this is also 0, this is also 0. So I am getting 2 is equal to 3 c3, so c3 is 2 by 3. So you have come to know how we have evaluated c1, c2 and c3. Therefore in this case, under these conditions, I have got c1 is 0, c2 is 0, and I have got c3 is what? 2 by 3. When the conditions were given by these conditions, this is not visible to you. y0, 0 means the value of y at x0. Y dash 0 is 0 means y dash is 0 at x0. Y double dash 0 is 2, that means d2y by dx is 2 when x is 0. Okay. So what was the solution? So required solution was, I will write again because I have rubbed it. Required solution is, it is y is equal to repeated root c1 plus c2x plus c3, c1 plus c2x plus c3 x square, c1 plus c2x plus c3 x square, it is e raised power minus 2x. Now you will use these values here, use these values, you have found these values, use these values here, you will use these values. This is y, c1 is 0, it is 0, it is plus 2 by 3 x square e raised power minus 2x. So required complete particular solution is with no c1, no c2, no c3. It is, we say it is not a general solution because we have got particular values of c1, c2 and c3. So y is particular solution. Y is 2 by 3 x square e raised power minus 2x. This is the solution of this problem. This was also an interesting problem where you get all the constants. The roots were also here repeated. You have got c1, c2 from these three conditions. Therefore, this is y is equal to 2 by 3 x square e raised power minus 2x. With this, I conclude the parts where right hand side was 0. Where we solve the linear differential equation with constant coefficient, the right hand side is 0. Now we will be dealing very important with this. Let it be lecture number 7. I will soon share lecture number 7. There I will take when right side is not 0, it is a function of x. The solution will contain two parts, y is equal to complementary function plus particular integral. Now you know how to find out the complementary function. Complementary function is nothing. Complementary function is simply when we write the right side 0, we solve it. It is this, like these solutions what you did in lecture number 5, lecture number 4 and 6, so on. Now the main thing is how to find out particular integral. For finding out the particular integral, I will share some formulae. I will derive some formulae so that in some cases you have to remember the formulae. In certain books, you are given the formula list for finding out particular integral, 10 or 12 formulae. It is very easy to remember them, but I will just derive some of them so that you will not commit it memory. You will also know how they exist, these results. Then after finding out particular integral, how to find out particular integral, we may conclude this linear differential equation. Till then, I say goodbye to you. Thank you very much, dear students.